Good morning, everyone. Thank you for joining us today. In our last deep dive, Automation Unleashed, we looked at robots as these incredible, self-contained machines. But what happens when we break them out of their silos? Today, we're exploring that next giant leap, the connected machine.
And that quote right there, that really gets to the heart of it. The true revolution isn't just about making one robot smarter. It's about creating a network where they all learn together. When they can share data and offload their thinking, they're not just one machine. They're benefiting from the collective experience of thousands, even millions of others. This is the big shift from simple automation to genuine evolving intelligence.
This is the big question we're tackling today. And to really answer it, we need to dive into this powerful trifecta that's making it all possible: the Internet of Things, the cloud, and the edge. We're going to explore how these three technologies are converging to create a level of intelligence that is completely reshaping entire industries right before our eyes.
To build our connected machine, we're going to use a biological analogy that I think works perfectly. So, first things first, we need to give it a nervous system. What's that foundational layer that allows an automated system to actually sense and feel the world around it?
Well, the answer is the Industrial Internet of Things, or IIoT for short. You see, before any system can be intelligent, it first has to be aware. And that's exactly what IIoT does. It's about blanketing physical equipment, engines, pipes, robots, you name it, with sensors, turning the physical world into a massive, continuous stream of digital data. This data, well, it's the lifeblood. It's the fuel for everything that comes next.
Now, many of us are probably familiar with consumer IoT, right? Your smart thermostat, your doorbell camera, that kind of thing. But the industrial version, it is a completely different animal. The core idea is similar, sure, but the requirements are worlds apart.
I mean, the demands on industrial IoT are just on another level entirely. We're talking about ruggedized sensors that have to survive being baked, frozen, and rattled to pieces on a mining truck, not sitting on a comfy living room wall. They need pinpoint precision, maybe measuring fractions of a degree inside a blast furnace. And the security stakes? They're enormous. A hacked toaster is an inconvenience. A hacked power grid? That's a potential catastrophe.
So what's the ultimate goal of collecting all this data? It's to create something really cool, a digital twin. Think of it as a perfect, real-time digital replica of a physical operation. And it's built using data from everything you can imagine. Vibration sensors that predict when a machine will fail, process monitors that check chemical compositions, and even AI-powered cameras that act as tireless quality inspectors on a production line. Of course, implementing this isn't always a walk in the park. If you're building a brand new factory, what we call a greenfield project, you can design all this smart tech in from day one. But most of the world is brownfield, factories full of decades-old, rock-solid, but completely dumb equipment. So a huge part of the IoT revolution is about retrofitting these legacy machines, adding new non-invasive sensors and gateways to bridge that gap between the analog past and the digital future. So the key takeaway here is that IIoT isn't just about collecting data. It's about creating a living, breathing digital model of a physical operation. It provides the ground truth, the sensory input for all the higher-level intelligence we're about to talk about. It is, quite literally, the nervous system of our connected machine.
All right, so our machine now has a nervous system. It can sense the world in incredible granular detail. But a nervous system on its own is just noise. It's useless without a brain to process it all. So how on earth do we handle that massive torrent of data and the insane computational demands of modern AI?
This is where cloud robotics comes into the picture. Think about it. An individual robot's onboard computer has limits: finite power, memory, and storage. Cloud robotics gets around this by connecting the robot to the virtually limitless resources of the cloud. In this model, the robot is the physical body out in the world, doing the sensing and acting, while the cloud acts as this incredibly powerful off-site brain that does all the heavy cognitive lifting.
And what kind of heavy lifting are we talking about? Well, a perfect example is training a complex AI model. This takes a staggering amount of computational power that would be impossible to cram onto a robot. So instead, the robot just collects data, sends it up to the cloud for the heavy-duty training, and then gets a compact, super-optimized model sent back down. This same logic applies to things like large-scale mapping for navigation or running thousands of complex simulations.
And this brings us to what is, hands down, the most transformative aspect of cloud robotics: fleet learning. This is the magic that allows a whole group of robots to learn from each other's experiences. It creates this powerful network effect where the entire fleet gets smarter and smarter over time.
And the absolute best example of this in the wild is Tesla's autopilot system.
The process is really quite elegant. Every Tesla on the road is basically a sensor-packed robot on wheels. When it encounters a tricky or unusual situation, what engineers call an edge case, it uploads a little snapshot of that event to the cloud. That real-world data is then fed into the central AI model to help it learn.
And that one little snapshot doesn't exist in a vacuum. It joins millions of other edge cases sent up from the entire global fleet. This creates a massive, incredibly diverse training data set that no team of test drivers could ever hope to replicate.
So after the central AI model is retrained with all this new data, the new, smarter version is pushed out to the entire fleet through an over-the-air software update. Think about that for a second. Every driver, just by using their car, is implicitly contributing to the education of the entire hive mind. It's a total paradigm shift. We've gone from programming one machine at a time to nurturing a collective intelligence that improves itself.
Okay, so we've got a sensory nervous system, and we've got this incredibly powerful collective brain in the cloud. We should be all set, right? Well, not quite. What about tasks that need an instantaneous reaction? A brain that's hundreds of miles away has its limits. Our connected machine also needs local reflexes.
And this is a critical question. You might be thinking, if the cloud has all this power, why not just do all the processing there? The answer comes down to one fundamental, inescapable limitation that's governed by the laws of physics: latency. The time it takes for data to travel to a distant cloud server and back might only be a fraction of a second, but in the world of high-speed robotics and automation, a few hundred milliseconds is an eternity.
This is precisely why we need edge computing, the idea of moving computation closer to where the data is actually generated. And there are 4 key, non-negotiable reasons for this. First, latency. A self-driving car cannot wait for a cloud server's permission to hit the brakes. Second, bandwidth. Trying to stream terabytes of raw sensor data to the cloud 24/7 is just not practical or affordable. Third, reliability. Critical functions have to keep working even if the internet connection goes down. And finally, privacy. A lot of sensitive data simply needs to stay on-site.
So it's really important to see the edge and the cloud not as competitors, but as partners in a tiered architecture. Let's see how it works. At the very bottom, we have Tier 1, the device edge. This is the computation that happens right there on the robot or the IoT device itself. It's responsible for the most time-critical tasks, those immediate reflexive actions and the low-level control loops that keep things running smoothly second by second.
Okay, moving one tier up, we have the near edge. Imagine a factory or a smart building. It might have a small server rack right there on the premises. This near-edge computer can pull in data from many local devices and run more complex analysis than a single robot could, but without the latency of sending it all the way to the public cloud. It's like a local supervisor. And then, finally, at the very top of the pyramid, we have the cloud. The cloud is still the ultimate destination for long-term data storage, massive-scale analytics, and, as we've already seen, that supercomputer-intensive job of training huge AI models. It sits at the top, leveraging all the pre-processed work done by the lower tiers.
And this entire tiered setup is what enables the modern AI workflow, which you can boil down to a simple mantra: train in the cloud, deploy to the edge. You take a massive AI model, train it in the cloud with tons of data and computing power, then you optimize it, shrink it down, and deploy that lean, fast version to the edge devices. Those devices then use the model for real-time decision-making, or inference, and send valuable new data back up, closing the loop and making the whole system smarter over time.
Let's make this really concrete with a smart building example. You've got thousands of sensors monitoring temperature, light, and whether people are in a room. An edge computer inside the building runs a model that makes instant decisions, like dimming the lights and lowering the AC in an empty conference room. That's a real-time, energy-saving reflex. Only summarized data, like maybe the total energy usage per day, gets sent to the cloud for long-term trend analysis and to train even better models to deploy back to the edge.
Okay, so let's take a step back. We've built our machine, we've given it a nervous system with IoT, a central brain with the cloud, and local reflexes with the edge. Now let's put all 3 of these components together into one single cohesive system.
This brings our biological analogy full circle, doesn't it? The IoT acts as the distributed sensory nervous system, constantly feeding the machine information about the physical world. The cloud serves as the powerful centralized higher brain, the home of deep learning and collective intelligence. And finally, the edge acts as the local high-speed reflex arc, enabling instant autonomous action right where it's needed.
And this right here is really the ultimate takeaway. This architecture isn't just about making one machine a little bit smarter. It's about creating entire systems that are vastly more capable than the sum of their parts. Systems that can learn, adapt, and optimize themselves on a scale that was pure science fiction just a decade ago.
So, in short, if you remember nothing else, remember this. IoT provides the awareness, the cloud provides the collective brain for deep learning, and the edge provides the real-time reflexes. Together, they are the foundation for the next generation of intelligent automation.
And that brings us to a final, pretty provocative question to leave you with. As these automated systems become more intelligent and more autonomous, as they begin to form their own collective mind, what then becomes the role of the human mind in this new world?
That very question is going to be the central focus of our next deep dive series. We're going to explore the new skills that will be required, the deep ethical challenges we're going to face, and what the future of work might look like in an increasingly automated world. I really hope you'll join us for that discussion.
Thank you so much for joining us today. The connected machine isn't some far-off future concept. It's the architecture being designed and built right now. To continue exploring where this incredible technology is headed, make sure you subscribe to our channel Tech, AI, and Beyond. We'll see you next time.